Okay, I'm going to jump back to 3.5 because you might have noticed that I skipped 3.4 and 3.5. I'm going to talk about 3.4 at the very end of chapter 3 because it's just talk about some applications. So I just wanted to go over the concepts first, and then we're going to talk about the applications later. Might be useful in this one, but I'm going to actually talk a little bit out of 3.5 in here as well. Oh, sorry, 3.4. Okay, so 3.4, 3.5 is about higher derivatives. Higher derivatives. What do you mean by higher derivatives? Higher derivatives. Now we need higher derivatives in certain cases, especially in engineering. I know a lot of applications that higher derivatives are required. The higher derivative means that you found function y equals f of x. The first derivative is denoted by f prime of x, or you sometimes you call y prime or dy over dx in terms of x, right? Y prime. And the higher derivatives, you have d over dx of f prime of x. The derivative of the derivative. That's called second derivative. Okay. It's denoted by f double prime of x. Okay. Or sometimes it's y double prime. Or in this case, d over dx squared y. Second derivative. This is called the second derivative. And you may have sometimes the third derivative. So you can find d over dx of f double prime x, which is f triple prime of x, which is also denoted by y triple prime. Also, you can write d cube over dx cube y. This is the third derivative. And these are called higher derivatives, right? Now, to have this derivative or the second derivative, your f prime x should be differentiable. Right? We talk about differentiability, right? What do you mean by differentiable? What do you mean by differentiable? What is the meaning of differentiability? How do we know that the function is differentiable or not? That limit of h goes to 0, when limit h goes to 0, f of x plus h minus f of x divided by h should exist. That limit should exist. If the limit does not exist, that means the function is not differentiable, right? Sometimes at some points, the limit does not exist. On those points, the function is not differentiable. But sometimes we have entire domain of function f of x, we have the limit. The limit exists. So that in that case, we call the function is differentiable, right? So the functions, if the function is differentiable, then you have the first derivative. If the first derivative is differentiable, then you have second derivative. If the second derivative is differentiable, then you have the third derivative. And you can go over and over, on and on to the nth derivative. Okay. But it is not necessary. In this case, we go to up to maybe like second or third derivative. Now let me point you out a practical example. I think I talked about in one of the videos, the previous class on Tuesday, a motion of a car, right? A car moving from zero velocity to some velocity, acceleration, right? Accelerating is increasing velocity, right? Now, if I draw the same thing, right? If something is accelerating, if I put the displacement time curve, right? Now, velocity v is equal to the time derivative of displacement, right? If the displacement is function of t, displacement is function of t, right? You can measure how far the car traveled with the time. Okay, and you can plot how faster the car moved by looking at t equals 0, the car was at s equals 0, and at t equals 1, it is at x equal 2, right? Or so on and so forth, right? So I can use that at t equals 0, the car is at s equals 0, and at t equals 1, it is at s equals 1, right? And t equals 2, it is at s equal 2, right? Something like that. So I can join these points. I can draw a curve, right? So what is the slope of the tangent drawn to this curve at any point? What does that represent? The slope of the tangent represents, what does that represent? We talk about the slope of the tangent line to the curve. It represents the derivative. So what is the derivative of change in distance over change in time is equal to what? What is it equal to? Change in displacement over change in time.
Velocity.
Velocity, very good, right? How faster the car is moving, or speed, right? So that means the slope of the curve at certain points equal to velocity at that time, right? We can get that. And we can find that slope. Can we find the slope? We can find the slope, right? If we find the derivative at those points, we can find the slope at those 2 points, right? Does that make sense? And I call this what? S prime, the slope, right? So this is S prime at T1, right? Here, the slope is S prime at T1. This is S prime at T2. Does that make sense? We did this one, right? Now, what I can do is, I can plot, this is just an example. I can plot S prime with time. What is actually S prime? S prime is velocity, right? S prime is velocity, right? So I can plot that S prime because I know at T1, S prime is equal to S prime T1, right? Prime is equal to, so this axis is S prime. So I find this value, I find the slope, right? Find the slope, and I put S prime of T1, right? S prime of T1, that is here, right? And I can find T2, right? This is T2, and I can find S prime of T2. This is S prime of T1, right? I can find that as well here. And I can plot that curve as well, right? Now, what is this actually? What does the curve represent? What does this represent? The first derivative. What is the first derivative of displacement? The name, what is this guy? V. Velocity. Now this curve represents velocity. Now I want to find the derivative of this one. What does that mean? That is the S double prime or V prime. Okay. So I can find the derivative of this one, right? I can find the derivative of this one. So the slope of this case is what? dV over dt. Or I can, in other words, it's ds prime over dt. That is what? That is SV prime or S double prime. Does that make sense? Does that make sense? So, what is dV over dt? The rate of change of velocity is equal to what? How fast the velocity is increasing? What does it matter? How is it related to the physics?
That's acceleration.
Huh?
That's acceleration.
Acceleration. So this is called acceleration. So if you find the slope to the curve at that point represents the acceleration at that time. Does that make sense? If the acceleration is constant, then how does this line look like? If the acceleration is constant, what is the shape of the S prime curve? Straight line. If the acceleration is 0, then this curve a flat one, right? Good. So that's a practical example, right? You have displacement. First derivative of that is velocity. The second derivative of that is the derivative of velocity, which is acceleration. Okay, does that make sense? Right? That's where we use them in our subjects. Okay, let's. Is there any question based on that? I'm just giving you an example of where we use these higher order derivatives. There are many other instances. Okay. When you're doing mechanical engineering, you'll see heat transfer. The rate of heat transfer through a solid can be mathematically modeled as second derivative of temperature. Okay. So those are the applications. So mathematical modeling is required to analyze problems before you do anything. Before you make anything, you have to do simulations, or you have to calculate and see what the answer is, and then you do and test it. Right? The old school method is to try and do, make something and blow it up. Right? But people learn engineering from those experiences and came up with equations, right? So then you can model things, and then you can learn a little bit and get a ballpark value, and then produce something, and then test it and go from there, which saves you a lot of money and time. A lot of money and time. Okay. Still, we use model testing. Without model testing, we cannot do anything. But mathematical modeling is important, so you kind of achieve halfway or more to the actual design with the mathematical modeling, and then start from there and go forward to the actual design. All right. So that's what we should be doing. Okay. So let's look at some examples. Okay, these are some examples in your book. You are given f of x equals x squared plus 1 over x plus square root of x. You are asked to find f double prime x. The second derivative. Find the second derivative. First, find the first derivative and differentiate it once again and find the second derivative. So I want to find d over dx f of x, or which is called f prime of x. So you find d over dx, right? X squared plus 1 over x plus square root of x. So this is d over dx x squared plus d over dx 1 over x plus d over dx x to the power half. Or you can write this 1 over x as x to the power negative 1. So we can solve this, right? What is the first term? What is the derivative of the first term? The first term, yeah, 2x. Yes, very good. Now you can do it correct straight off. 2x plus, what is this one? Negative x negative 2, right? Negative 1, that's negative, right? Plus, this is half x to the power negative 1/2. And that's our f prime of x, or the first derivative. And when you take second derivative f double prime of x, that is d over dx f of x. Or you can write d squared over dx squared f of x. Now you want to find the derivative of derivative. D over dx 2x minus x to the power negative 2 plus half x to the power negative half. Then you find d over dx 2x minus d over dx x to the power negative 2 plus half d over dx half x to the power 1/2. Now what is the derivative of the first term? 2. Good. And the second term, you have negative 1 in front of that, and you have negative 2 x to the power negative 3. Good. Plus, you can take half out, right? And then you have 1/2, negative 1/2 x to the power negative 3/2. Does that make sense? So you have 2 plus 2x negative power 3 minus 1/4 x to the power negative 3/2. Okay, makes sense? Any questions? Good. Then example, the second example. Find f triple prime x for f of x equals 3x to the power 5 minus 2x to the power 2 plus 7x to the power negative 2. Okay, you find the third derivative. All good? You find it? Okay, so let's do this. First, you find the first derivative, f prime of x, right? Which is d over dx, 3x to the power 5 minus 2x squared plus 7x to the power negative 2. So you get the first term is 3 times 5 times x to the power 4, right? Minus 2 times 2x plus 7 times negative 2 x to the power negative 3, right? So from that I get 15 x to the power 4 minus 4 times x minus 14 times x to the power negative 3. Are we all good? Then f double prime of x, that is d over dx, 15 to the times x to the power 4 minus 4 times x minus 14 times x to the power negative 3. Okay. So if I get the second derivative, this is 15 times 4 times x to the power cube, x cube minus 4, right? Minus 14 times negative 3 x to the power negative 4. right? And from that I get 60 x cubed minus 4 minus 42, right? 42 plus 42 is minus 3, 14, and negative sign become positive 42 x to the power negative 4. Are you with me? Okay. So then triple prime of x. Well, d over dx 60 x cubed minus 4 plus 42 x to the power negative 4. We have 60 times 3x squared minus 0, right? Plus this will be 42. 42 times negative 4 x to the power negative 5. So we have 120 x squared minus 168 x to the power negative 5. This is a triple prime x. And if you ask to find the value at certain point, you can do that as well. Right? Does that make sense? Any questions? Jason, you have questions? I didn't get third derivative, yes. Oh, yeah. 60 times 3 is 180. Very good. I missed that one. Absolutely right. 180. Yes. 60 times 3 is 180. Not 16, 120. 120 is 2. Any questions? You're good? So you know that we can talk about the behavior of the graph by looking at the derivative, right? For example, we know that the derivative, sometimes you have positive slope, right? In this side. And then you have negative slope, right? And then you have zero slope, right? So whenever you have a function, right, that has maximums or minimum. Maximum or minimum. If you say you are given a function, let's say f of x equals x cubed plus 2x squared plus 5x plus 7 or something like that. Find me the maximum of this one. Maximum, find me the x value at the maximum of this function or something like that. So at maximum or minimums, right? At maximums or minimums, what would happen to the derivative of the function? So how does a maximum look like? If you have a maximum value of the function, how does it look like in a graph? Huh? The highest point, right? So at the highest point, what would happen? It goes like this and then turns back, right? So what do you think that the derivative at this point for the slope? What? 0. Slope is 0. So that means the derivative, the first derivative should go to 0 at maximums and minimums. At the minimums, this should do like that. Not only those 2 points, but also sometimes you might have seen functions goes like this. What do you call that point? So this is a, what is that? This is the minimum. This is the maximum. This is a minimum, right? What do you call this one? That's called saddle point. It's like a saddle. Or saddle, right? Saddle point, a flat point, right? Now that point also you have zero slope. That means your derivative is zero. Now, if I'm asked to find the maximums and minimums of a curve, right? Maximum of the curve, when I find the derivative, right? And make the derivative zero and find the x locations. For example, if I have x squared plus 2x plus 1, f of x. Now find me the maximum, the x value at the maximum. That's the question. So what would I do is, I would find f prime of x. What is f prime of x? 2x plus 2. Now, at a maximum point, this f prime x should be equal to what? What? 0. Oh, good. Now this is the equation, right? So where does that x prime of x go to 0? At which x value? When you solve this equation, 2x plus 2 equals 0, you get x equal -1. So at x equal -1, the graph has a maximum or minimum or saddle point. Okay? This function has a maximum or minimum or saddle point. If derivative goes to 0, that means it should have either of these, right? So how would I make sure that this is the maximum or minimum or saddle point? How do I do that? Now look at when the function comes to a maximum, what would happen before the x equal, let's say this is x equal -1, right? Let's say this equal x equal -1. Actually, the graph should be on the other side. This function has a minimum, not a maximum, but I don't know. Okay, I don't know. But what I do is, what is the behavior of f prime x before for the values less than -1? It's a positive one, right? Right? And then you have a -1. Okay? You have a positive slope first, derivative is positive, and the derivative becomes negative. So it turns 0 and becomes negative. Does that make sense? What I'm saying? So if I draw, now this is f of x, right? If I draw f prime of x, how does it look like in this point? Now, if I draw this one, you have a positive derivative, positive slope, and it became 0, and then it went negative. So if I draw, it starts with positive and becomes 0 and something like that, right? So this is what? This is the curve of f prime x, right? Curve of f prime x. So what is the slope? What is the sign of f double prime x? What is f double prime x? What is f double prime? F double prime x is the slope of this curve. Does that make sense? Does that make sense? What is the slope of this curve? Is positive or negative? Negative. Now what? If I find f double prime or prime x, if that is negative, what is that point? Is it maximum or minimum? What is this one? It is positive, turn negative, turn 0 and negative. And when you draw f prime x, it looks like this. Are we all agree with that one? So what is the sign of this slope? The sign of this slope is negative. That means your value of f double prime f x should be, what is this one? Negative. So if you have a 0 f prime x at that point and a negative f double prime x, what is the point? What kind of point is that? It's a maximum. Now let's learn about the next one. Then it may be clear for you. Now when it comes to minimum, right? The slope is negative first, and it turns 0 and becomes positive. So it starts with negative and goes to positive, right? So this is f prime x. So what is the slope of the f prime x? Positive. Slope of f prime x is equal to the slope of f prime x is equal to f double prime x. So we have a positive f double prime x. We have 0 f prime x and positive f double prime x. That means it's a minimum, right? And then look at this one. You have positive. I'm going to take a different color. You have a positive slope here and became negative, sorry, 0, and then you become again positive. Does that make sense? You had something positive and reducing it to negative, sorry, 0, right? 0 line is this one, 0, and then it turned back to negative, sorry, again positive, right? So you had positive and turn back to positive again. Okay, so you had a positive slope, sorry, yeah, you had a positive value and it's still positive, right? The slope is still positive. That means the sign, if the sign of the slope doesn't change, you have a saddle point, right? Does that make sense? So this information is useful in many different ways, right? So you are given a function and you find the max, whether you have a maximum or minimum, find those values or something like that. There are a lot of applications in any field of science. So if I bring out a population growth or something like that related to biology, right? This Connor is here. So the population growth can be given as a differential equation or any function, and then you can find where does that population become maximum by looking with the time, right? By looking at the derivative of the time derivative of that function, it becomes 0. And to make sure that it's a maximum, you have to find that second derivative and see whether second derivative is negative at that point. If the second derivative is negative at that point, then it's a yes, maximum. Okay, if the sign doesn't change, and second derivative is negative, and then the sign doesn't change, it's going to be a saddle point. Does that make sense? Yes.
Can the saddle point be flipped around to where it's like negative?
Yes. It can do that. Yes. Does that make sense? So that's something extra that I had to mention, because in some cases you are given this function. So you have an example that's actually example 6 in your textbook. It looks, you are given a function, a curve like this. And you are asked to find the, and there are two solutions. This is fx with x. This is identify 1 and 2 figure B, the graph of f prime or f double prime for the function f. So you have two functions given, one in green, which looks like this, and then there's another one in red. It's like this. So this is number 1, this is number 2. So it says identify curves 1 and 2 in figure B. So this is B. This is figure A. As the graphs of f prime or f double prime for the function f in figure 4A. So this is figure A has function, and we need to identify whether any of these related to f prime or f double prime. So look at f prime first, right? So if you look at f prime, you have a positive, so negative slope here, right? And it becomes 0 here, and then becomes positive, right? So which curve represents something like some behavior like that? The red curve here in this one. So curve number 2 related to what? F prime of f, right? This is f prime of x, the red one, right? So if you have f double prime, we don't know actually. We cannot find f double prime with this information. So f prime is increasing function in graph must be 2. Since f double prime is the rate of change of f prime, and f prime is increasing. So yeah, so if f double prime, so now what is f double prime? This is f prime. So if you have f prime, then your f double prime is the slope up to that, right? The slope actually increasing. It's also always positive, right? Always positive. So it should be like this. The curve 1 could be f double prime, could be, but we don't know. Could be. But definitely this one is f prime. This one is not, this is not f prime. This could be f double prime, but we don't know. So make sure that you get that kind of a understanding about the curves and how the f prime, f double prime changes will be useful. Does that make sense? Okay. Let's work out some other problem with let's see. Yeah, this is not very difficult one, but let's no, the trigonometric functions are not given here. We can use function with exponent. So we have something like that, number 15, 3.5, 15 is y equals x to the power 5 times e to the power x. Find y double prime and y triple prime. find y prime. Okay, so we're going to work on this one. So f prime is, this is the product rule, right? You can put the product rule. D over dx, x to the power 5, e to the power x. First derivative 5x4 e to the power x plus x to the power 5 e to the power x. Does that make sense? So let me write it in detail. So first you take e to the power x and then take the derivative of x to the power 5 plus you take x to the power 5 out and take the derivative of e to the power x. So you have 5 times, you have e to the power x, 5 times x to the power 4 plus x to the power 5 e to the power x, right? And then you have y double prime. You have to derivate this d over dx, dx 5x to the power 4 plus d over dx, x to the power 5 e to the power x, right? This is again y, right? This is y. Same thing, right? So you can put that's y and y prime, right? So if I do this one, it's going to be e to the power x. Can take y out, d over dx, x to the power 4 plus 5 times x to the power 4 d over dx e to the power x plus d over dx y, that means y prime. You can put y prime there because we already found y prime here. This is y prime. This one is y prime. Does that make sense? Because this is one. You can substitute this one here later. Does that make sense? Let me know if it doesn't make sense. I can do product rule again. This is y, right? Instead of this, I wrote y. So I keep it like that. It may be easier for me to do this. So because this is dy over dx. And this is d squared y over dx squared. Okay. And what do you get? This is 5 to the power 5 e to the power x, and then 4 x cubed plus 5x4 ex. Plus y prime. Okay. And then I find the third derivative. I can go another round. D over dx. This is dx. Oh, I can put 20 x cubed e to the power x plus 5 x to the power 4. 5x to the power 4. Oh, hold on. Did I do something wrong? That's right. No, I'm right. Okay. This x to the power 4 e to the power x plus y prime. Okay. And then I can write 20 e to the power x d over dx x cubed, right? Plus 20 x cubed d over dx e to the power x plus 5 e to the power x d over dx x to the power 4 plus 5 x to the power 4 d over dx e to the power x plus d over dx y prime. That's y double prime. Okay. So you can substitute y double prime and y prime, and then you can go from here 20 e to the power x 3 x squared plus 20 x cubed e to the power x plus 5 e to the power x 4 times x cubed plus 5 x to the power 4 e to the power x plus d y prime over dx. And you can substitute dy prime over dx, that is this one. The answer. It's a long one, right? Probably you can find this. What is this term? That's also x double prime, right? Y double prime. So y double prime minus y prime, actually. So this is d squared y over dx squared minus y prime. And this is d squared y over dx squared plus the rest. You just need to do the same thing over and over again, right? Yeah, so with that, I finish out. Before that, you have any questions based on that? Second, no, here, no, you don't have to. I just use because it is convenient, because if I put, now, if I didn't have this one, right? If I didn't put this one, I would put this and I had to go another two more terms. Expanding more. So it's easier to put, whenever you find something, it is easier to put in that. If you don't figure that out, that's okay. You can just work as regularly as possible. So it doesn't matter. You don't have to. But if you find some kind of relation like that, it is easier to use it because your expression gets shorter.